We're going to illustrate step 2 with the reaction. We have carbon dioxide plus hydrogen gas combining to form CH3OH, which is a liquid. Assume the reactants and products are at 1 atmosphere and 298 Kelvin. That's good, so we can do the standard entropy change and the standard enthalpy change. We're going to calculate the standard enthalpy change for the system for the reaction. See, we're back on enthalpy. Then assume that this amount of thermal energy is transferred reversibly to the surroundings, so we can use this definition of entropy change of the surroundings. And we replace Q, which is the heat, with delta H of the surroundings. And finally, we put a negative sign in here. Okay, see how the Q got replaced by delta H? And the negative sign comes from the fact that the direction of energy flow for the surrounding is opposite to that of the system, right? If it flows into the system, that means it's flowing out of the surroundings. So we have a negative in there that will take care of that number for us. Let's now calculate our standard entropy change for this reaction, for the surroundings. We have our reaction here, and here we have a number of standard enthalpy changes with the H, and notice how they're in kilojoules, where entropy changes are in joules. We have our equation for the system. We start with the products, and all we have is methanol up here, and that is negative 238.6. There's a 1 in front of it, right? We assume, so there's just 1 mole. Then we go to our reactants. Carbon monoxide has a 1. Hydrogen has a 2. Don't care about hydrogen because it's a 0 here. It's a pure element. So we put the negative 110.5 in here. We subtract out, and we get a standard enthalpy change of the system of negative 128.1 kilojoules. To find the standard entropy change for the surroundings, that's equal to negative delta H system divided by the temperature we're at. And what temperature are we at for standard conditions? Well, 298, so we put that in. We put in our standard enthalpy change here. We do the division, and notice the negative sign. Okay, we showed that the last slide, and we get a delta S naught surroundings of 430 kilojoules per Kelvin, or if you move the decimal over and get rid of the kilo prefix, you get 430 joules per Kelvin. Let's wrap this problem up now, and here's the methanol reaction. Here's the equation we've been using, and we found that delta S naught for the surroundings was 430 joules per Kelvin, and that delta S naught for the system is minus 332 joules per Kelvin. Is the reaction product favored or not? We just add those two together, and we come up with a positive number. And if you have a positive entropy change for the universe, that means it is product favored or spontaneous, that's the other word for it, as written at a temperature of 298 Kelvin and 1 atmosphere. Let's work another problem. We've got this magnesium carbonate going to magnesium oxide plus carbon dioxide, and we want to calculate the standard entropy change for the universe. We've already shown that the standard entropy increase for the system, or change, is 174.9 joules per Kelvin. Now we want to determine delta S naught surroundings first, and then delta S naught universal, and we can indicate whether the reaction is product favored at 298 Kelvin. So we have our standard enthalpy changes here. We go to our balanced chemical reaction here. We start with the products, and we have 2 products, and we have carbon dioxide and magnesium oxide. Each one of them have a coefficient of 1, so you can see we just put in the standard enthalpy changes there, and then we subtract out the reactant. And the reactant also has 1 mole. So we put in the negative 1095.8 kilojoules per mole. We multiply them by the moles, and we just wind up with kilojoules. So we get where standard enthalpy change for the system is 100.6 kilojoules, or 100,600 joules. We then find our standard enthalpy change for the system by taking the negative of that and dividing it by the temperature we're at, which is 298 Kelvin. And we get delta S naught surroundings is negative 337.5 joules per Kelvin. Let's finish up here. We have our delta S naught for the universe. We have to add the two values for the system and the surroundings. And we get a negative 162.7 joules per Kelvin. This tells us that it is not spontaneous or product favored at this temperature because delta S naught for the universe is less than 0. Earlier we said we had some ways of predicting whether it would be favorable, and we thought it would be in this case because of the gas production, right? Over here, there's no gas. Over here, you have 1 mole of gas. So if we just went by that thumb rule, we should have said the entropy would increase, and this would be a spontaneous reaction. However, those were just guidelines. You actually have to do the calculation to determine whether the reaction is really thermodynamically favorable. You have to do the math.